All right, welcome back to the definite integral. This is video 6 of section 6.2 in our book. And what I want to do now is I want to talk about two problems that we talked about earlier, and I'm going to relate them to the integral that we've been talking about here. So let's start with a constant function. You may remember that we had a problem where we had a ship that was sailing at a constant rate. And it sailed at that rate from some time to some other time. And the question was, how far did the ship sail? And we figured out that it was just the area of that rectangle. So what I want to look at now is I want to say, let's set this function at f of x equals a constant to represent well, in this case, the speed of the ship, but it doesn't matter. And what happens when I take the integral from a to b of f of x dx when f of x is a constant function? So this becomes the integral from a to b of c dx. And looking at the graph, we can see that, well, this has a height of c, and it has a width of b minus a. And so we end up with the value of this integral being c times b minus a. So anytime we see the integral of a constant, we can just take that constant value, take the difference of the indices, and multiply them together. Boom, we're done. Okay, let's move on. And the next problem that we had talked about was an accumulator function. And you may remember that we talked about snowfall. And we talked about an accumulator function being, how do we represent the amount of snow falling? So what we're going to do now is we're going to say that the accumulator function, we had figured out that the amount of snow that fell was the area under that snowfall curve. So this is the integral from some time when our function starts to some time when we're interested in of f of t dt. Now, notice we've got two different variables going here. T is time. F of t is what is happening with respect to time. Remember WRT, with respect to. And in our example, it was the snow is piling up and it changes over time, whereas x is some intermediate time that we are interested in looking at. So let's do an example to illustrate this. Here's our example. Let's say that our function of time is 1 plus 2t for the interval 1 to 6. So time is going from time 1 to time 6. And our accumulator function is the integral from 1 to x. Remember, this is going to be a variable function because we want to know, well, what's happening, how much at time 2, how much at time 2.5, and so on, of 1 plus 2t dt. So let's draw a quick graph. We've got a linear function that starts at 1 and goes up by 2. We're interested in the interval 1 to 6. Notice now that x has to be between 1 and 6. We said that time was available for 1 to 6, but that was when we were defining this function. It's only a valid function from time 1 to time 6. Now we're saying that we want to be able to choose some value of x, but it has to be in that interval. So let's take a look. What do we know about right here? Well, this is height 3. What do we know about right here? This is height 1 plus 2x. And this is width x minus 1. We have a trapezoid. Remember that the area of a trapezoid is base 1 plus base 2 divided by 2 times the height of the trapezoid. Our trapezoid here is on its side, so a of x is going to be equal to 3 plus 1 plus 2x divided by 2 times the height, which is x minus 1. Doing a little simplification, we see that this is x plus 2 times x minus 1. And we can multiply this out to get x squared plus x minus 2. And what we now know is that the accumulator function for this problem, the integral from 1 to x of 1 plus 2t dt, is equal to x squared plus x minus 2. If we want to know how much has accumulated from time 1 to time x, we take our x, we plug it in, and we now know the answer. Okay, my students, go ahead and do exercise 29. That's from the constant value portion of this video, and do exercise 33, which is the accumulator portion. And we will see you in the next video. Thanks for watching.